is the most familiar world beyond Earth. Yet familiarity can hide the scale of what separates a visit from a life. Its light has followed human evenings for longer than any written record. It rises over cities, deserts, farms, and oceans, close enough to show changing phases without a telescope. And because people have already walked there, the lunar surface can seem almost settled in the imagination, as though the hardest part was reaching it once. But the Apollo landings were brief encounters with a place that never had to support ordinary human time. Apollo 17, the longest of the surface missions, remained on the moon for about 75 hours. Every meal, tool, breath of oxygen, and planned task had been prepared in advance, and the crew left before the environment could become a permanent condition of life. A settlement changes the question. It is no longer enough to ask whether a spacecraft can land, whether a suit can hold pressure, or whether a crew can work for several days. The new question is whether a complete human system can continue through weeks, years, repairs, illness, fatigue, and the small failures that become audible when people stay anywhere for long enough. A short mission can carry nearly everything it expects to use. A lasting community must replace what is consumed, repair what is worn, recognize problems before they spread, and keep enough reserve capacity for events that do not appear on a schedule. The difference is not only duration, it is the change from a carefully timed expedition into an environment where daily life must renew itself. On Earth, much of that renewal is supplied without being noticed. The atmosphere presses against the body, carries sound, moderates heat, and absorbs part of the radiation and debris arriving from space. The moon has only an extremely thin exosphere, with roughly a quadrillion times fewer molecules in a given volume than Earth's atmosphere. Its surface receives no meaningful protection from that gas. Sunlit ground near the lunar equator can reach about 260 degrees Fahrenheit. In darkness, the temperature can fall near minus 280 degrees. The moon also lacks a strong global magnetic field, leaving the surface exposed to a radiation environment very different from the one beneath Earth's atmosphere and magnetosphere. None of this means that lunar settlement is impossible. It means that life there would not be supported by the moon itself. It would be supported by layers of engineering that must perform the work of a planet. Walls would become atmosphere. Radiators and insulation would become weather. Water stores would become part of the radiation shield. Electric power would stand in for sunlight at the wrong hour. Air filters would protect lungs from dust that Apollo crews found capable of entering cabins, irritating eyes and airways, damaging equipment, and wearing against suit materials. And beneath every visible machine would be another system waiting behind it. Spare parts, medical care, food production, waste recycling, communication, exercise, and the human ability to live inside a limited space without losing judgment or purpose. So the path ahead is not a story of conquering the moon. It is a careful examination of dependence. To understand what it would really take to live there, we will move outward from the human body, through the suit and habitat, into power, water, food, construction, medicine, and the surrounding lunar landscape. At every step, the same principle will return in a different form. On the moon, survival is not one machine working well. It is every necessary machine continuing to work together. The first permanent lunar home would be defined by a boundary only a few centimeters thick. On one side, air would move through ducts. Water would remain liquid. Voices would travel normally across a room. On the other, there would be no breathable atmosphere, no weather, and no pressure to support the ordinary chemistry of the human body. A door on Earth usually separates one familiar place from another. A lunar airlock would separate two entirely different physical worlds. Every trip outside would begin by preparing that boundary. The crew would check seals, oxygen supplies, cooling loops, batteries, communications, and the condition of each suit joint. The airlock would close behind them, and the air inside would be recovered into storage tanks rather than released. Pressure would fall in a controlled way until the outer hatch could open onto the surface. The suit would no longer be clothing. It would be a compact habitat shaped around a person. Inside it, oxygen would be supplied at a pressure lower than sea level on Earth, while layers of fabric, insulation, restraint material, and protective coverings held the suit together against the surrounding vacuum. A liquid cooling garment would carry heat away from the body. Carbon dioxide would have to be removed continuously. Moisture from breath and perspiration would need to be managed before it condensed on a visor or interfered with equipment. All of these functions would continue while the person walked, bent, lifted tools, and tried to work through pressurized gloves. The vacuum itself is often imagined in dramatic ways. A person exposed to it would not burst apart, but the situation would still become critical within seconds. Without pressure and oxygen, useful consciousness would fade quickly. Water in exposed tissues could begin to vaporize at body temperature, a process known as ebullition, while swelling and severe oxygen deprivation followed. A settlement would therefore be designed around the assumption that pressure failures must be detected early and contained locally. Habitats would be divided into sections. Hatches could isolate a damaged compartment. Sensors would listen for small leaks. Emergency masks and portable oxygen would remain within reach. The larger challenge, however, would arrive through the airlock after every successful excursion. It would arrive as dust. Lunar soil is not soil in the biological sense. It contains no roots, worms, decayed leaves, or generations of microorganisms. It is regolith, a layer of broken rock and glass produced by impacts across immense spans of time. Without rain, rivers, or wind, the fragments have not been rounded. As sand grains often are on Earth, many retain sharp edges. Some contain glassy structures formed when impacts briefly melted surface material. Solar ultraviolet, light and charged particles also alter the electrical condition of grains near the surface, helping dust cling to suits and equipment. Apollo crews encountered this material during visits lasting only days. It coated boots and legs, worked into joints, scratched surfaces, and entered the lunar modules with the returning astronauts. It carried an odor they compared to spent gunpowder, though the smell probably arose after fresh lunar material met the cabin atmosphere. For a settlement, dust would not be an occasional inconvenience. It would be part of the daily flow of work. Imagine the outer hatch closing after a surface repair. The suit that has returned is pale grey around the knees and boots. Fine particles rest in folds around bearings and along tool edges. When the airlock is repressurized, some of those particles lift and move. They can settle on filters, electrical contacts, screens, storage racks, and skin. The safest airlock may therefore resemble a cleaning system more than a simple chamber. Tools could remain outside whenever possible. Suit ports might allow a spacesuit to stay attached to the exterior of a vehicle or habitat, so the astronaut enters through a hatch in the back without bringing the suit indoors. Electrostatic systems could move charged dust away from visors, radiators, and solar panels. Brushes, vacuum devices, and replaceable coverings could remove part of what remains. None of these methods is likely to create a perfectly clean habitat. The goal would be control rather than complete removal. That distinction matters because lunar dust could affect both machinery and health. Abrasive grains can damage seals and moving surfaces. Dust on a radiator changes how heat leaves a system. Dust on an optical instrument reduces the clarity of its view. Dust across a solar panel lowers the power it can produce. Inside the body, the smallest particles may present another problem. Apollo astronauts experienced temporary irritation after dust entered their cabins, but their exposures were brief. The consequences of breathing small amounts repeatedly for years are still uncertain. Researchers study lunar samples and simulated regolith to understand how particle, shape, chemistry, and surface reactivity might affect lung tissue. The concern is that fine, angular particles can reach deep regions of the lungs where removal is difficult and may contribute to inflammation or cellular damage. A lunar habitat would need several layers of defense. Air filtration would remove suspended particles. Surfaces would be designed for cleaning, without scattering dust back into the room. Work clothes might remain in transition areas. Medical monitoring could look for changes in breathing before symptoms became obvious. Equipment maintenance schedules would account for abrasion even when a mechanism still appeared to work. This would change the rhythm of ordinary life. Returning home would not mean opening a door and stepping inside. It would mean inspection, cleaning, pressure checks, and careful handling of everything brought back. A loose tool bag, a damaged boot covering, or a seal with one embedded grain could matter more than it would in any workshop on Earth. Over time, the settlement would learn the behavior of dust at its own site. Regolith differs from place to place. Material near a young crater may not behave exactly like material on an older plain. Polar dust may spend long periods at temperatures far below those of equatorial terrain. Local experience would become part of survival, recorded in maintenance logs, and passed from one crew to the next. There is a human continuity in that kind of knowledge. Sailors once learned the hidden character of coastlines by returning to them repeatedly. Desert communities learned where fine sand entered walls and machinery. Polar crews learned which materials remained dependable after months of cold. A lunar community would build its own practical traditions in the same way, not from legend, but from accumulated attention. The first lesson would be simple. The surface could never be treated as an extension of the home. Every journey outward would cross a pressure boundary. Every return would bring part of the moon back with it. And the long work of living there would begin each day by keeping those two worlds carefully apart. Beyond the airlock and the dust, the next challenge is written into the length of a lunar day. From sunrise to sunset at most places on the moon, nearly 2 Earth weeks pass. Then the sun slips below the horizon, and night continues for roughly another 2 weeks. The full cycle takes about 29.5 Earth days. This creates a world that does not warm and cool in the familiar rhythm of morning, afternoon, evening, and night. Heat accumulates for days, then it escapes for days. Near the lunar equator, sunlit ground can rise to temperatures near 260 degrees Fahrenheit. After dark settles, the surface can fall toward minus 280 degrees. The exact temperature depends on location, terrain, sunlight, and the properties of the ground. But the broader problem remains the same. The moon has almost no atmosphere to redistribute heat from one region to another. On Earth, air currents move energy, clouds reflect sunlight and trap infrared radiation. Oceans absorb heat during warmer periods and release it later. Even dry ground transfers energy into the air above it. The moon has no comparable system. A rock in sunlight receives energy directly from the sun. A nearby rock in shadow may remain bitterly cold. The boundary between heat and cold can be sharp enough to exist across a short distance. For a settlement, temperature would not be managed by waiting for the weather to change. It would be controlled continuously by insulation, heaters, cooling loops, heat exchangers, and radiators facing space. The habitat itself would generate heat. People release warmth. Computers, lights, pumps, agricultural equipment, and air processing systems all add more. Inside a sealed structure, that heat cannot simply drift away into the surrounding air, because there is no surrounding air. It must be collected and carried to an external radiator. A radiator works by emitting infrared energy into space. Its large surface allows heat from the habitat to leave as radiation. The process is dependable, but it is also sensitive to orientation, dust, sunlight, and damage. A radiator aimed into a cold, dark sky can reject heat efficiently. A radiator warmed by direct sunlight becomes less effective. Dust covering its surface changes how it absorbs and emits energy. A puncture or failed cooling line can threaten every system connected to it, so even something that sounds passive, a panel releasing heat, becomes part of the settlement's life support network. During the lunar day, reflective surfaces and insulation would help prevent excess solar heating. Equipment might operate behind sun shields or inside covered structures. Cables, seals, lubricants, batteries, and electronics would need to remain functional while nearby surfaces became hot enough to damage ordinary materials. When night arrived, the problem would reverse. The ground beneath exposed equipment would begin losing heat into space. Metal structures would contract. Batteries would become less efficient. Some polymers would stiffen. Lubricants could thicken or stop flowing. Components designed to fit together at warmer temperatures could shift slightly as they cooled. The movement would be small, but it would happen again and again. Every lunar month, exposed structures would pass through a wide thermal cycle. Expansion during daylight would be followed by contraction in darkness. Over many cycles, these repeated changes could loosen connections, strain joints, and encourage cracks to grow from minor imperfections. Engineers already designed spacecraft for thermal cycling. Satellites repeatedly move between sunlight and Earth's shadow. Robotic missions operate on planets and moons where temperatures change dramatically. A permanent settlement would extend that challenge across a much larger system. It would include living modules, landing pads, power stations, communications equipment, mining machines, storage tanks, vehicles, and long networks of cables and pipes. Each part would have its own preferred temperature range. Each material would expand and contract at a slightly different rate. Wherever different materials met, the interface would need to absorb those differences without leaking, separating, or wearing out. The most obvious source of energy would be the sun. Solar panels have powered spacecraft for decades. They contain no turbines and require no fuel once installed. On the moon, sunlight is strong and unobstructed by clouds or atmospheric haze. For nearly 2 weeks, an equatorial solar field could produce power for much of the day. Then sunset would reduce its output to nothing. The settlement would still need electricity. Air must continue moving. Carbon dioxide must continue being removed. Water must remain within safe temperatures. Communications, medical equipment, food storage, computers, lighting, and environmental controls cannot be turned off for half a month. Energy gathered during daylight would therefore need to be stored on a scale far beyond a brief nighttime reserve. Batteries are one possibility. During the day, solar arrays could charge large banks of them. During the night, those batteries could release power gradually. But storing enough electricity for 2 weeks of continuous operation would require a considerable mass of batteries. They would need thermal control, fire protection, monitoring, repair, and eventual replacement. Their useful capacity would slowly decline with repeated cycling. A settlement could reduce its nighttime demand by postponing manufacturing, excavation, and other power-hungry activities until daylight. Yet the systems supporting human life would remain active every hour. Other forms of storage could share the load. Solar energy might be used to split water into hydrogen and oxygen during the day. Those gases could later be recombined in fuel cells, producing electricity and water during the night. Energy could also be stored as heat in insulated materials or through mechanical systems designed for the lunar environment. Each approach would trade one difficulty for another. Batteries require large quantities of manufactured cells. Fuel systems need tanks, plumbing, and careful handling. Thermal storage requires insulation and conversion equipment. Mechanical storage introduces moving parts into a dusty landscape. The location of the settlement could make the problem easier. Near the lunar poles, sunlight arrives at a low angle and moves around the horizon. Some elevated ridges receive illumination for long portions of the lunar year, while nearby crater floors remain in permanent shadow. A base positioned near one of these well-lit areas could generate solar power for much longer intervals than a base near the equator. Short periods of darkness would still occur, depending on the exact terrain and season. But the storage requirement could become far more manageable. This is one reason the South Polar region attracts so much attention. Sunlit high ground may offer access to power, while nearby shadowed craters may contain water ice. The arrangement is promising, but not convenient. Solar panels work best where sunlight reaches them. Water may be found in places the sunlight never touches. The two resources could be separated by steep slopes, broken terrain, and regions of deep cold. Power might have to travel through cables from an illuminated ridge to machines operating inside shadow. Those cables would cross uneven ground and endure repeated stress. Mobile equipment might carry batteries from charging stations into darker regions. Small nuclear systems could provide local power where sunlight never arrives. Nuclear fission offers a different kind of stability. A compact reactor could produce electricity through day and night, independent of the sun's position. Its steady output could support life support systems, medical equipment, communications, and emergency reserves even when solar generation was unavailable. Would not need to be large enough to power an entire growing settlement by itself. A network might combine solar arrays for abundant daytime energy, with nuclear units providing a dependable baseline. Yet a reactor brings its own infrastructure. It must be transported safely. It must be positioned far enough from living areas to limit exposure while remaining accessible for monitoring and maintenance. Its waste heat must be carried to radiators. Its electrical systems must survive dust, vacuum, radiation, and temperature change. The settlement would also need a plan for failure. If a solar field were damaged by dust or an electrical fault, another source would have to take over. If a reactor shut down, batteries or fuel cells would need to carry the critical load. If a power cable were severed, sections of the habitat would need local reserves. Redundancy would not be an optional feature. It would be the shape of the entire power system. On Earth, a blackout is usually an interruption. On the Moon, a prolonged blackout would begin changing the habitat immediately. Ventilation would weaken, carbon dioxide would rise, water lines could freeze in exposed sections, food could spoil, internal temperatures could move outside safe limits, communications could fail at the moment, outside assistance was most needed. For that reason, power generation, energy storage, and thermal control would be designed as one connected system. Heat produced by one machine might warm another. Water stored for drinking could also serve as thermal mass. Agricultural lighting could be scheduled around available energy. Waste heat from a reactor might support industrial processing or help keep equipment warm. Nothing useful would be allowed to remain useful in only one way. The Moon's long day does not simply create hot afternoons and cold nights. It sets the rhythm of construction, power use, maintenance, movement, and rest. A lunar home would survive that rhythm by building a smaller, engineered climate inside a world that has none. And every light glowing behind its walls would depend on energy gathered, stored, and protected long before the darkness arrived. Power can keep a habitat warm, move its air, and hold back the lunar night. But electricity alone cannot stop what passes through the walls. The Moon lies beyond most of the protection that surrounds Earth. It has no dense atmosphere overhead and no strong global magnetic field redirecting charged particles around the surface. A person standing outside is exposed to a stream of radiation that arrives from the sun, from distant regions of the galaxy, and from secondary particles produced when that radiation strikes the lunar ground. Some of it comes steadily, some of it arrives in storms. These two patterns create different problems. Galactic cosmic rays form the persistent background. They are atomic nuclei moving at very high energies, many of them protons, with smaller numbers of heavier nuclei such as carbon, oxygen, silicon, and iron. Their origins are connected to energetic processes beyond the solar system, including the remnants of exploded stars and other environments capable of accelerating particles across interstellar space. They do not arrive from one direction. They approach from across the sky, passing through the solar system at all hours. The sun's magnetic field influences how many of them reach the inner solar system. During periods of stronger solar activity, the expanded and more disturbed heliospheric environment can reduce part of the cosmic ray flow. During quieter portions of the solar cycle, more of these particles may reach the moon, but they never disappear. A cosmic ray can cross the wall of a lightly shielded habitat and continue into the body. As it travels through tissue, it can ionize atoms along its path, leaving a narrow trail of molecular disruption. Cells repair much of this damage as they repair damage caused by natural background radiation on Earth. The concern grows when exposure continues month after month and year after year. Radiation risk is not limited to one organ or one outcome. It may contribute to cancer, cataracts, cardiovascular injury, changes in the central nervous system, and other effects that researchers continue to study. The biological response depends on the particle type, its energy, the tissue it crosses, the accumulated dose, and the individual receiving it. This complexity makes lunar radiation difficult to describe with a single number. A dosimeter can record the energy deposited in material. Medical models can estimate how that exposure may affect tissue. Yet the most energetic heavy particles do not behave like the X-rays used in a hospital. They can create concentrated damage along their tracks and produce secondary particles when they collide with matter. Shielding them is not as simple as placing a thick plate of metal around the habitat. When a high-energy particle strikes the nucleus of an atom, inside dense shielding, the collision can break both into smaller fragments. Those fragments may continue forward as a shower of secondary radiation. The original particle loses energy, but the interaction spreads that energy into new directions and new particle types. A wall can therefore reduce one part of the radiation field while creating another. Materials rich in hydrogen are often useful because hydrogen nuclei are light and contain no neutrons. Water, polyethylene, stored food, and certain plastics can help slow charged particles while producing less damaging fragmentation than many heavier materials. This gives ordinary supplies a second purpose. Water tanks might be arranged around sleeping quarters. Food stores could line the walls of a protected compartment. Waiting to be processed could be placed where its mass contributes to shielding. The settlement would treat every kilogram not only as cargo, but also as part of its protective geometry. Still, no practical wall would stop every galactic cosmic ray. The goal would be to lower exposure, monitor it, limit time in less protected areas, and place the most frequently occupied rooms behind the greatest amount of material. The second radiation pattern is less constant and more urgent. The sun occasionally releases large numbers of energetic particles during periods of intense activity. Solar flares and coronal mass ejections are related but distinct events, and not every eruption sends a dangerous particle storm toward the moon. When the geometry is unfavorable, however, energetic protons can reach the lunar environment and raise radiation levels rapidly. A person outside during a major event could receive a serious dose before an ordinary surface mission was complete. The danger would not always be visible. The sky would remain black. The ground would look unchanged. There might be no physical sensation announcing that charged particles were crossing the suit. The warning would come through instruments, solar observatories near Earth, and elsewhere in space would watch active regions on the Sun. Detectors around the Moon would measure the local particle environment. Forecasting systems would combine these observations, looking for eruptions and for the first faster particles that can precede the main arrival. A settlement would need to remain connected to that network continuously. When an alert was issued, people working outside would stop what they were doing. Rovers would turn toward shelter. Airlocks would be prepared. Equipment might be left in place if bringing it back delayed the crew. Just inside the base, everyone would move toward a storm shelter. This room would not need to be large. It would need to be close, well shielded, and capable of supporting the entire crew for as long as elevated radiation persisted. Water tanks, food, supplies, and thick structural material could surround it. Independent ventilation, communications, sanitation, and emergency power would allow the room to function even if another part of the habitat failed. The storm shelter might also serve as the sleeping area during ordinary days. Beds require little open floor space, and sleep occupies many hours of every 24-hour cycle. Placing the crew there would increase the amount of time spent behind the strongest available shielding without turning radiation protection into a separate daily task. For long-term settlement, the best shield may be the Moon itself. Lunar regolith is available everywhere. Moving it is difficult, but it does not have to be launched from Earth. Robotic machines could excavate it, carry it, and build layers over prefabricated modules. Bags or hollow blocks filled with local material could form protective walls. A buried habitat could place meters of regolith between its occupants and the open sky. The covering would also moderate temperature changes and provide some defense against micrometeorites. At first, construction might be simple. A cylindrical module would land on the surface. Robots would inspect it, connect utilities, and gradually pile regolith over most of its exterior, while leaving airlocks, radiators, antennas, and maintenance access points clear. Later structures could be designed to fit into shallow trenches. Inflatable volumes might be deployed and covered after they were pressurized. Local materials could be sintered into blocks or fused into protective shells. The habitat would begin to disappear into the landscape. From a distance, the settlement might not resemble the bright domes often imagined in illustrations. Much of it could lie beneath low mounds of grey material, with only communication towers, solar arrays, vehicles, and shielded entrances remaining visible. This is not a retreat from the Moon. It is a practical way of joining its surface. Human beings have used Earth as protection for a very long time. Homes have been built into hillsides, beneath turf, inside rock, and behind thick earthen walls. The reasons were different in each place, but the principle was familiar. The ground surrounding a shelter changes the environment inside it. On the Moon, that old architectural instinct would take on a new purpose. The soil would not keep out wind or rain. It would stand between living tissue and the radiation crossing space. Natural underground spaces might offer even more protection. Long ago, when the Moon was volcanically active, lava flowed across parts of its surface. The outer portion of a flow could cool and harden, while molten rock continued moving beneath it. After the interior drained away, a hollow passage remained. These passages are known as lava tubes. Orbital images have revealed pits that may be openings into larger underground structures. Some shaded portions of lunar pits maintain far more stable temperatures than the exposed surface. A deep tube could also place many meters of rock overhead, providing shielding from radiation and small impacts. The possibility is appealing. A natural cavern might offer a protected volume larger than anything humans could afford to launch or excavate during the early years of settlement. But an opening seen from orbit is not yet a home. Before people could live inside a lunar tube, robotic explorers would need to enter it. They would map the floor, ceiling, walls, and branches. They would search for loose rock, steep drops, unstable sections, and deposits of fine material. They would measure radiation, temperature, and the movement of dust. The communication underground would be difficult. Radio signals do not pass easily through thick rock, so relay devices would need to be placed along the route. Rovers might descend on cables or use specialized legs and wheels to cross broken terrain. Small flying vehicles could operate only with propulsion, since there is no air for wings or rotors. Even after a tube was judged stable, people could not simply seal the entrance and fill the entire cavern with air. The surrounding rock may contain fractures and unknown pathways. Pressurizing a huge natural space would require an immense quantity of gas and would place stress on surfaces that were never shaped to hold internal pressure. A more realistic approach would place sealed habitats inside the tube. Modules could be assembled within the protected cavern, using the overhead rock as shielding, while their own walls contained the atmosphere. The interior space around them would remain a vacuum. Cables, pipelines, storage, workshops, and vehicles could occupy the surrounding floor without being exposed to direct sunlight or the full radiation environment of the surface. Windows might be replaced by cameras and displays. Light from outside could be carried inward through fiber optic systems or reproduced through carefully designed illumination. The settlement sky would be an engineered ceiling, while the actual lunar sky remained beyond layers of stone. Living underground would solve several problems, but it would create others. Access routes would need to remain open. Emergency exits would be difficult to build. Dust could collect in sheltered areas. Communication equipment would require redundancy. The psychological effect of spending years without a direct view of the surface would need to be considered from the beginning. Protected observation rooms might be built near an entrance. Cameras could provide continuous views of Earth and the surrounding terrain. In interior spaces could use changing light, plants, color, and depth to prevent the habitat from feeling like a narrow machine. Radiation protection would shape not only the walls, but the culture inside them. People would learn where the safest rooms were. They would know the sound of an alert and the quickest route to shelter. Personal dosimeters would become as ordinary as watches. Surface schedules would depend on solar conditions. Medical records would include accumulated exposure across years. Some residents might accept more risk for scientific or construction work. Others might spend most of their lives beneath shielding. Pregnancy, childhood, illness, and recovery could lead to stricter exposure limits than those used for healthy adults. The settlement would make these decisions without complete certainty. Human beings have never lived for years on the lunar surface. Models can estimate risk, and experiments can reveal mechanisms, but the first long-duration residents would still be entering a biological environment without a full human history. Their shelter would therefore need room to improve. More regolith could be added, water walls could be rearranged, new materials could line older modules. A small storm refuge could become a larger protected district as the settlement expanded. Over time, the safest part of the base might grow into its true center. The moon would remain above it, receiving the steady passage of particles from the galaxies and the occasional storms of the sun. Beneath the surface, air would circulate through buried rooms. Lights would follow an Earth-like day. and people would continue their work behind walls, made partly from the world they had come to inhabit. The shelter could hold pressure, block much of the radiation, and keep its rooms within a livable temperature. Yet one part of the settlement could not be sealed away from the moon. Gravity would remain. At the lunar surface, gravity is about 1/6 as strong as it is on Earth. A person with a mass of 180 pounds on Earth would press against a lunar floor with the weight of about 30 pounds. The mass would not change. The body would still resist acceleration in the same way. But every step, lift and landing would happen under a much smaller downward pull. For a short visit, this can look almost liberating. Apollo astronauts learned to move with a loping stride, allowing both feet to leave the ground before falling back in long, measured arcs. Equipment that would have been difficult to carry on Earth became easier to raise. A stumble unfolded more slowly, leaving more time to react. The same gravity that makes movement playful for a few days could reshape the body across a lifetime. Human tissue is always responding to use. Bone is removed and rebuilt. Muscle fibers grow or shrink according to the work demanded of them. The heart and blood vessels adjust to the effort required to move blood through the body. Even the systems that guide balance depend on a lifetime of experience with a familiar downward direction. Earth's gravity is part of the environment in which every human body has developed. You can notice its presence without standing. Resting in bed, the body still has weight. The mattress pushes upward while gravity draws downward. Bones, muscles, circulation, and the organs suspended within the torso all occupy a world with a constant pull. On the moon, that pull would be smaller every hour of every day. Bone would be among the first concerns. It may appear solid and fixed, but living bone is active tissue. Cells called osteoclasts remove older material, while osteoblasts help build new matrix and mineralize it. Mechanical strain is one of the signals influencing that balance. On Earth, ordinary life provides repeated loading. Walking places force through the hips and legs. Standing loads the spine. Climbing stairs, carrying groceries, and rising from a chair all tell the skeleton that strength is still required. In 1/6 gravity, daily movement would send a weaker message. Experience aboard orbital spacecraft shows what happens when normal loading nearly disappears. Astronauts in microgravity can lose bone mineral, especially in weight-bearing regions such as the hips, legs, and lower spine. Exercise reduces the loss, but it does not make the body believe completely that it remains on Earth. The moon is not microgravity. A resident would stand on a floor and feel weight. The legs would still work. The skeleton would still receive some loading. The unanswered question is whether 1/6 is enough. No person has lived in lunar gravity for months, much less years. The Apollo missions were too brief to reveal long-term adaptation. Bed rest studies on Earth and experience in orbit can offer clues, but neither reproduces a body walking, sleeping, and working continuously under 1/6 gravity. The response might slow after an early period of bone loss. It might stabilize at a new level, or some regions could continue losing strength unless daily countermeasures supplied forces closer to those found on Earth. A settlement could not wait for symptoms before responding. Bone loss is often difficult to feel while it is happening. The first clear sign could be a fracture during a fall, a return flight, or rehabilitation under stronger gravity. Residents would therefore be monitored over time. Medical teams could track bone density, blood chemistry, muscle strength, posture, and movement. Small changes recorded across months would guide exercise schedules, and habitat design would become part of life support. A lunar gym would need more than light-free weights. A metal mass weighs less on the moon, just as a person does. So an Earth-style barbell would provide only 1/6 of its familiar load. Resistance would need to come from springs, elastic systems, flywheels, pneumatic devices, or machines that oppose motion directly. Squats, presses, heel raises, and pulling movements could load the skeleton along several directions. A treadmill might use a harness to draw the body firmly toward the belt. Cycling could maintain cardiomyofascial endurance, though it would offer less direct loading to the bones. The equipment would be designed not simply for fitness, but for preserving the ability to live elsewhere. That distinction would shape every session. A resident might feel capable while moving through a lunar corridor, yet still be losing the strength needed to tolerate Earth's gravity. Training would maintain a connection to a planet the body was no longer experiencing. Muscle would follow a related pattern. Muscles remain costly tissue to maintain. When the body encounters lower demands, it can reduce fibers that seem unnecessary. On the Moon, standing requires less effort. Walking lifts the body through a weaker gravitational field. Objects have the same inertia, but supporting them against the floor is easier. Without resistance training, the muscles of the legs, hips, back, and trunk could gradually lose size and strength. Postural muscles might change because the effort of holding the body upright would be different. Movement habits would also adapt, favoring the bouncing gait that works efficiently in low gravity. The cardiovascular system would receive another kind of lesson. On Earth, the heart must move blood through a body stretched vertically inside a strong gravitational field. When a person stands, blood tends to shift downward. Blood vessels tighten, the heart adjusts, and the nervous system makes rapid corrections to maintain flow to the brain. In lower gravity, those pressure differences would be smaller. The body might no longer need the same degree of cardiovascular control. Over time, blood volume, heart function, and the reflexes that stabilize pressure could adjust to the easier environment. Astronauts returning from orbit sometimes experience dizziness or weakness. When they stand under Earth gravity again, their bodies must relearn how to manage the downward shift of blood. Lunar residents might face a related problem after long stays, although the degree of change in 1/6 gravity remains unknown. A person returning after several months might recover with rehabilitation. After many years, the process could be longer. Some residents might find Earth uncomfortable or medically difficult, not because the journey home was impossible, but because their bodies had become better suited to the Moon. This possibility gives lunar gravity a subtle power. It would not injure someone in a single dramatic moment. It would act through adaptation. The body is remarkably willing to become appropriate for the place where it lives. Balance and orientation would also change. The inner ear measures rotation and linear acceleration, while vision and pressure through the feet help the brain interpret position. On Earth, these signals have agreed with one another since infancy. On the Moon, a jump lasts longer. A falling object accelerates more gradually. The effort of beginning a movement remains connected to mass, while the force pulling the body downward is reduced. At first, this can produce awkward motion and misjudged steps. With experience, the brain builds a new model. Corridors, stairs, handholds, and workspaces would be shaped around that model. Ceilings might be higher because a small push can lift a person farther than expected. Sharp overhead edges would be avoided. Equipment would be secured even when it felt light, because its mass could still cause injury once it began moving. Falls would deserve careful attention. A person descends more slowly on the Moon, but the surface and interior structures remain hard. Reduced bone strength could make an ordinary fall more serious after years of adaptation. Lunar medicine would therefore connect architecture, exercise, and monitoring rather than treating them as separate concerns. Artificial gravity is sometimes proposed as a way to provide stronger loading. A rotating room can create an outward acceleration that feels like gravity along its outer wall. In principle, Residents could spend part of each day inside a centrifuge, exercising or resting while their bodies experienced a greater force. In practice, a human-scale rotating habitat would require space, structural strength, power, and carefully controlled motion. A small centrifuge turns quickly and can create uncomfortable differences between the forces at the head and feet. Moving the head while rotating may cause disorientation or nausea. A larger system would reduce these effects, but would be harder to build on the moon. Early settlements may rely more on targeted exercise than on full rotating living spaces. Later communities could add larger centrifuges if evidence showed that 1/6 gravity was not enough to preserve health. The greatest uncertainty would concern development rather than decline. It is one thing to ask how an adult body changes after leaving Earth. It is another to ask how pregnancy, infancy, and childhood would proceed in lunar gravity. Mammalian development involves gravity-sensitive processes, from balance and movement to bone formation and circulation. Human evidence for healthy development at 1/6 gravity does not exist. Any discussion of children born on the moon must therefore remain cautious. Their bodies might develop in ways well suited to lunar life. They might also face risks that cannot be predicted from adult spaceflight. A permanent community would need years of biological research before reproduction could be approached responsibly. A child raised there might never experience Earth as a natural home. The planet would be visible in the sky and present in family stories, but its gravity could feel overwhelming to a body formed under a weaker pull. This would make gravity more than a number in a physics lesson. It could become part of identity. The first settlers would remember the weight of rain-soaked clothing, the effort of climbing a hill, and the pressure of feet against an earth floor. Later generations might know those sensations only through machines that briefly recreated them. For everyone, the central task would remain the same. The habitat would have to support not only breathing bodies, but bodies capable of staying healthy inside a world that was steadily teaching them to change. And before those bodies could remain there for long, the settlement would need to solve another daily requirement: finding enough water, air, and food to keep renewing them. A human settlement can carry tools, machines, and replacement parts from Earth. It cannot remain dependent forever on shipments of every breath, every drink, and every meal. The first lunar crews would arrive with stored supplies. Oxygen would wait in tanks. Water would be packed into containers and distributed through the habitat. Food would be sealed, labeled, and counted carefully against the mission calendar. That works when departure is already planned. A permanent community must turn consumption into a cycle. Water offers the clearest example. The human body uses it continuously, not only through drinking, but through cooking, hygiene, cooling systems, medical care, and food production. Every resident releases water into the habitat through breath, perspiration, and waste. On Earth, those streams disappear into plumbing, soil, rivers, and the atmosphere. On the Moon, they would remain inside a closed inventory. Humidity removed from cabin, air could be condensed and purified. Wastewater from washing could pass through filters and chemical treatment. Urine could be processed to recover most of its water. Even moisture released by plants would return to the system through the air. The settlement would not make new water each day. It would keep using much of the same water again. This is already part of life aboard orbital stations, where recovery systems reduce the amount that must be launched from Earth. A lunar base would push that principle further, because every lost liter would eventually need to be replaced. Perfect recovery is not realistic. Filters retain residue. Maintenance releases small amounts. Water becomes trapped in waste products or construction materials. Leaks occur. Some processes consume or disperse it in ways that make recovery difficult. A growing settlement would therefore need a local source. The strongest evidence for accessible lunar water lies near the poles, where sunlight never reaches the floors of some craters. These permanently shadowed regions remain cold enough for water molecules delivered by comets, asteroids, solar wind chemistry, or ancient lunar processes to become trapped over long periods. The water is not expected to exist as a clear underground lake. It may be mixed through regolith, concentrated in patches, bound to grains, or buried beneath dry surface material. Its amount and physical form can vary greatly from one location to another. Before mining begins, robotic missions would need to map those differences at close range. A rover could drill into the ground, warm samples, and measure the gases released. Radar and neutron instruments could search for hydrogen-rich deposits across larger areas. Small prospecting vehicles might test many sites before heavier equipment was delivered. The first water mine would likely be a careful scientific operation rather than a broad excavation. Inside a shadowed crater, machines would work without direct sunlight in conditions cold enough to weaken batteries, stiffen cables, and challenge ordinary lubricants. Power might arrive through lines from a sunlit ridge. A compact reactor could supply electricity locally. Some equipment might enter the crater briefly, then return to a warmer service area. Excavated regolith could be carried into a sealed chamber and heated. As the temperature rose, ice and other volatile compounds would turn into vapor. The vapor would move through a processing system where water could be separated, condensed, and purified. Every stage would require energy. Digging consumes power. Heating frozen soil consumes more. Pumps, seals, storage tanks, and purification equipment must continue working in vacuum and cold. The machinery would also need to avoid releasing valuable vapor back into space. The cost of extracting 1 liter might be high at first, yet that liter could serve several purposes. It could become drinking water. Electricity could split it into hydrogen and oxygen. The oxygen could support breathing, while both gases could be stored for fuel cells or used as rocket propellant. Water could circulate through cooling systems or line the walls of protected rooms as radiation shielding. A tank near the sleeping area would not be only a tank. It would be part of the habitat's defense. Oxygen may also be available from the ground itself. Lunar rocks contain large amounts of oxygen chemically bound within minerals. The difficulty is not finding the element. It is separating it from silicon, aluminum, iron, titanium, calcium, and other materials to which it is attached. Several extraction methods are possible. Some heat regolith in the presence of hydrogen or methane. Others melt it and pass an electrical current through the material. At high enough temperatures, the chemical bonds can be broken, while leaving metals or metal-rich products behind. The process would resemble a refinery more than a household life support machine. It would need furnaces, insulated reactors, electrical systems, gas collection, and careful control of dust. The high temperatures would place stress on containers and seals. Replacement components might be difficult to manufacture during the early years, but the reward would be important. Oxygen is a large fraction of the mass needed for breathing and propulsion. Producing it locally could reduce the amount launched from Earth and support vehicles traveling between the surface and lunar orbit. The remaining material might become useful as well. Iron, aluminum, silicon, and other elements could feed future manufacturing. Not every extraction process would produce pure metals ready for construction, but even rough local products could be used for shielding blocks, landing pads, glass, ceramics, or simple structural parts. The settlement would gradually learn to see regolith not as featureless dust, but as a complicated mineral resource. Food would be harder to close into a cycle. Packaged meals can support small crews for a long time, but they bring weight, storage limits, and dependence on resupply. Their nutritional quality also changes during extended storage. Some vitamins degrade, variety narrows. The psychological comfort of fresh food becomes more important as months pass. Plants could address part of this problem. Inside a sealed growing room, crops would receive water, carbon dioxide, nutrients, and carefully timed light. Their leaves would release oxygen and water vapor. Their roots would take up dissolved minerals. The crew would gain fresh vegetables, while the habitat gained another biological component in its air and water cycles. The natural lunar day would not set the schedule. Artificial lighting would create mornings and nights suited to each crop. Leafy greens grow quickly and provide fresh texture, color, and micronutrients. Radishes and herbs require relatively little space. Dwarf tomatoes, peppers, beans, and strawberries could add variety. Potatoes, wheat, soybeans, or other calorie-rich crops would be more demanding but more important for true independence. A salad can improve a meal. It cannot sustain a settlement by itself. Producing most of the crew's calories would require a much larger agricultural system. Plants need room, light, water, nutrients, pollination, disease control, and time. Their unused stems and roots must be processed rather than discarded. Crop failure must be expected, with enough reserves to keep one poor harvest from becoming an emergency. Hydroponic systems could grow roots in nutrient-rich water. Aeroponic systems could suspend them in humid chambers and deliver nutrients as a mist. Both avoid the need to turn raw lunar regolith into soil. They also depend heavily on machinery. A failed pump can dry roots quickly. A contaminated water loop can carry disease through an entire crop. Sensors must track acidity, nutrient concentration, temperature, moisture, and dissolved oxygen. Lighting failures must be repaired before plants lose critical growth time. Soil-like systems may eventually offer greater resilience, but lunar regolith would need extensive treatment before it could support healthy agriculture. It contains no organic matter and no living community. Earth soil is crowded with bacteria, fungi, and small organisms that break down waste, release nutrients, and interact with roots. Those relationships are part of what makes soil fertile. A lunar garden would have to build that biology intentionally. Composted plant material could add carbon. Processed human waste could return nitrogen, phosphorus, and other nutrients after careful treatment. Selected microorganisms could support decomposition and root health. Over years, a manufactured soil might develop inside protected agricultural rooms. The process would begin with materials brought from Earth and continue through almost complete reuse. Nothing organic could be treated casually as garbage. A trimmed leaf would become compost. Food scraps would return to a processing system. Carbon dioxide exhaled by the crew would feed plants. Plant waste might support insects, fungi, or microbial reactors that produce food, fertilizer, or useful chemicals. Human waste would be among the settlement's most valuable and carefully managed resources. It contains water and nutrients, but also pathogens and compounds that should not return directly to crops. Treatment could involve heat, chemical processing, filtration, controlled biological breakdown, and repeated testing. The purpose would not be to imitate a simple natural ecosystem. It would be to create a monitored network in which biology and machinery supported one another. A greenhouse could also provide something less measurable. After months beneath shielding, a room of living plants would offer color, scent, changing shapes, and the small evidence of time passing through growth. New leaves would appear, flowers would open, fruit would ripen. For residents surrounded by metal, stone, and processed air, tending a plant might become one of the few daily tasks that did not feel entirely mechanical. Yet the plants would be part of the survival system, and that would change the relationship. A crop would be beautiful, but it would also be counted. Its water use, light demand, nutrient balance, and expected harvest would remain visible in the settlement's planning. The closed loop would never be completely closed. Certain nutrients would be lost. Equipment would wear down. Crop diversity would require seeds and genetic material. Medicines, electronics, specialized chemicals, and complex components would continue arriving from Earth for a long time. Self-sufficiency would not mean isolation from Earth. It would mean reducing the number of things whose absence could end the settlement. At first, nearly every critical supply would come from home. Later, water and oxygen might be produced locally. Then, construction materials, spare parts, and a larger share of food could follow. The transition would take years. Success would not arrive on the day the first habitat was occupied. It would emerge gradually, as each fragile supply line was replaced by a cycle that could be maintained on the Moon. Inside those cycles, the same molecules would move again and again. Water would pass from a tank into a cup, through a body, into the cabin air, through a condenser, and back into storage. Carbon dioxide would leave the lungs, enter a leaf, and return later as oxygen. Minerals would move from waste into roots, and from roots into food. Living there would mean becoming aware of exchanges that Earth usually hides. Nothing would truly disappear, and almost nothing useful could be allowed to leave. The first lunar settlement would not be finished when the crew arrived. It would begin as a collection of systems waiting to become dependable. Some structures would be launched from Earth in nearly complete form. Others would unfold after landing. Power cables would need to be connected. Airlocks would need to be tested. Radiators would need clear views of space. Antennas would be aligned toward Earth or toward relay satellites. Protective material would be moved into place around the living modules. Before anyone could call the site a home, it would have to pass through a long period of assembly. Much of that work would be better suited to robots. Machines could arrive months or years before the first residents. They could survey landing zones, smooth roads, place navigation markers, and prepare foundations. They could move regolith over habitat modules, inspect cables, and establish power connections before a human crew depended on them. On Earth, construction equipment is built for an environment rich in air, gravity, and easy access to repair crews. On the Moon, every machine would operate in vacuum, under abrasive dust, across large temperature changes, with replacement parts separated from the site by hundreds of thousands of miles. A robotic excavator might resemble a small terrestrial vehicle, but its design priorities would be different. It would need sealed bearings or mechanisms that tolerate dust. Its electronics would require radiation protection and thermal control. Its wheels or tracks would need traction on loose regolith without digging themselves into the surface. Motors would have to release heat without surrounding air to carry it away. Even simple tasks would unfold more slowly. Moving a pile of regolith requires a blade to enter the ground, collect material, transport it, and release it in a controlled layer. In reduced gravity, the soil weighs less, but its mass remains unchanged. Once a load begins moving, the machine must still control its inertia. Dust lifted by the blade does not billow in air, but particles can follow long ballistic arcs and settle across nearby equipment. Robotic work would therefore be planned around distance and direction. Excavation areas might be placed downrange from solar fields and radiators. Roads could be compacted or fused to reduce loose material. Sensitive instruments would remain covered while nearby machines were active. A settlement would gradually create cleaner paths through the landscape. Landing pads would be especially important. Rocket exhaust striking loose regolith can accelerate particles across large distances. During Apollo landings, dust moved rapidly beneath the descent stages and obscured the surface near touchdown. A larger lander, arriving near permanent infrastructure, could scatter material toward habitats, panels, antennas, and vehicles. Early pads might be formed by compacting the surface. Later versions could be sintered, using heat or microwaves to fuse grains into a harder crust. Locally produced, pavers might be placed by robots. Berms could redirect part of the exhaust and catch some of the material thrown outward. The settlement would need a safe distance between its landing zone and its living area, but not so much distance that cargo became difficult to transport. Every delivery would begin another chain of work. Containers would be unloaded. Pressure vessels would be inspected. Batteries, medical supplies, machine parts, food, and scientific equipment would be moved into storage. Some cargo would remain outside in shielded depots. Other items would pass through dust control areas before entering the habitat. Nothing would be accepted simply because it had survived the journey. A hairline crack in a pressure tank, damage to a connector, or contamination inside a fluid line could become serious only after the equipment was placed into service. Inspection would be part of arrival, and records would follow each component through its useful life. Maintenance would occupy more time than the first residents might expect. Pumps would wear, filters would clog, seals would age, dust would enter joints. Software would need updates, cables would loosen after thermal cycling. Valves would begin moving less freely. Sensors would drift away from accurate readings. A settlement that could build but not maintain itself would remain temporary. This is why spare parts would be as important as food or water. Some failures could be repaired with simple replacements. A bearing, a gasket, a circuit board, a length of tubing. Others would require specialized equipment that could not be stored in unlimited quantities. The inventory problem would be difficult. Bringing one spare for every component would add too much mass. Bringing none would make the settlement vulnerable to minor failures. Engineers would need to identify common parts across many systems so that one motor, valve, connector, or control board could serve several machines. Standardization would become a form of safety. A growing base would also need local manufacturing. At first, this might involve modest tools, machining equipment, welding systems, polymer printers, and devices for producing simple metal or ceramic parts. A damaged bracket, pipe fitting, protective cover, or tool handle could be made on site instead of waiting for a launch from Earth. More complex parts would remain difficult. Electronics, precision bearings, medical devices, and high-performance seals depend on manufacturing chains that span many facilities on Earth. Reproducing those chains on the Moon would take a very long time. Local production would begin with the parts that are heavy, simple, and frequently needed. Regolith could be fused into blocks, tiles, shielding panels, or road surfaces. Glass might be made from local silicate material. Metals extracted from minerals could eventually support beams, plates, and basic machine components. Even imperfect lunar materials could be useful when the alternative was launching structural mass from Earth. Three-dimensional printing would help, though it would not remove the need for engineering judgment. A printed part must still have the right strength, surface finish, and thermal behavior. A shape that looks correct may fail under pressure, repeated motion, or radiation exposure. Every locally made component would need testing. This would create a culture of careful repair. A technician might remove a worn part, measure it, produce a replacement, test that replacement in a controlled fixture, and only then return the machine to service. The same caution would guide work outside. A spacesuit allows a person to cross the vacuum, but it makes ordinary movement laborious. Pressurized gloves resist the hands. The suit limits bending and turning. Tools must be designed for use through thick fingers that tire over time. A bolt dropped on Earth usually falls nearby. On the Moon, it can bounce farther than expected and disappear into dust. A tool released without a tether may be difficult to recover. A small tear, damaged connector, or failing cooling loop can turn a routine repair into a return to habitat emergency. Surface work would therefore be slow by design. Each excursion would have a clear objective, a planned route, and enough reserve time to return before life support margins became narrow. Rovers could carry emergency oxygen, tools, communication relays, and temporary shelter. Work teams might remain within reach of a pressurized vehicle even when operating far from the main base. Robots would handle repetitive and hazardous tasks whenever possible. Humans would intervene where adaptability, judgment, and fine decision-making mattered most. Even then, the crew would need to know when to stop. Fatigue changes the quality of decisions. A tired person inside a habitat can rest. A tired person outside may grip a tool less carefully, miss a warning signal, or take longer to notice damage. The settlement's schedule would have to treat fatigue as a physical risk rather than a personal weakness. Medical care would follow the same principle. The moon is close enough for conversation with Earth, but too far for immediate evacuation. A trip home would take days under favorable conditions. Many medical emergencies cannot wait that long. The base would need its own diagnostic and treatment capability. Ultrasound equipment could provide images of internal organs without the mass of a large scanner. Blood tests and compact laboratory systems could identify infection, dehydration, inflammation, and changes caused by radiation or low gravity. Dental tools would be necessary because a cracked tooth or abscess cannot be postponed indefinitely. The crew would need training that extended beyond ordinary first aid. At least some residents would require advanced medical skills. Others would learn to assist with procedures, operate equipment, sterilize instruments, and maintain life support during treatment. Guidance from Earth could help, but the people on the moon would still have to perform the physical work. A communication delay of a few seconds is manageable during a careful consultation. It is less helpful during a sudden loss of blood pressure or an airway emergency. Medical planning would therefore emphasize prevention. Residents would be screened before departure. Chronic conditions would be monitored closely. Exercise, nutrition, radiation exposure, sleep, and mental health would be treated as connected parts of one system. Small problems would be addressed early before they became difficult to manage far from a hospital. Medication storage would require attention to temperature, radiation, and shelf life. Supplies would expire. Some drugs might degrade faster in the lunar environment. The pharmacy would need regular rotation and careful records. Surgery would remain possible but difficult. A protected room could become an operating space. Restraints would keep the patient and equipment stable in reduced gravity. Fluids would behave differently, and every instrument would need to remain organized. Recovery would occur inside the same confined settlement, where ordinary work continued nearby. The first lunar residents would accept that some risks could not be reduced to Earth standards. That truth would shape the kind of people who went. But courage alone would not be enough. The settlement would survive through preparation, repetition, and the willingness to give routine tasks the same attention usually reserved for dramatic events. A repaired seal, a tested valve, a cleaned connector, and a correctly stored medicine would rarely appear in the story told from Earth. On the moon, those quiet acts would be the story. The base would endure not because nothing failed, but because failure had been expected, noticed, and answered before it could spread. A lunar settlement would not be held together by machinery alone. It would also depend on people learning how to remain human, inside a place where nearly every ordinary rhythm had to be manufactured. On Earth, time arrives through changing light. Morning enters a room, afternoon shifts the color of a wall. Evening lowers the sky towards sleep. Even when clocks are ignored, the body receives these signals and adjusts itself around them. The moon offers no 4-hour pattern of its own. At most locations, the sun remains above the horizon for nearly 2 weeks and then disappears for nearly 2 more. A settlement would therefore create its own day. Lighting systems would brighten gradually at a chosen morning hour, become cooler and stronger during the work period, then dim and warm toward evening. Bedrooms would be shielded from equipment lights. Screens and control panels would reduce their brightness before sleep. Work shifts would keep emergency coverage without forcing the entire community into permanent night work. This would not be decorative lighting. It would be part of medicine. The circadian system influences sleep, alertness, metabolism, hormone release, immune function, and mood. When light arrives at the wrong time, the body can remain awake when rest is needed, or become drowsy while important work is underway. Over weeks, repeated disruption can reduce judgment and increase the strain of confinement. The settlement would monitor light exposure with the same seriousness given to exercise or radiation dose. Even with careful lighting, sleep would not always come easily. Fans would move air through the habitat at every hour. Pumps would cycle, valves would open and close. Computers, refrigerators, water processors, and carbon dioxide scrubbers would create a background of mechanical sound. Some of that sound would be reassuring. It would mean that air was moving and heat was leaving the rooms, but it would never fully disappear. A sleeping cabin would need acoustic insulation, personal ventilation, and enough separation from major equipment to allow the mind to release its constant attention. Each resident would need a small private space where the door could close and no one else needed anything for a while. Privacy would be limited, but it could not be treated as a luxury. In a confined settlement, social contact would be abundant and choice would be scarce. The same people would eat together, work together, solve emergencies together, and meet again in the corridor after every disagreement. On Earth, distance often helps relationships recover. A person can leave a room, walk outside, or spend a day among strangers. On the Moon, the available world may be a network of connected modules occupied by a small number of familiar faces. That closeness can create trust. It can also magnify irritation. Crew selection would need to value patience, self-awareness, and conflict resolution alongside technical ability. Training would include more than emergency drills. Residents would practice making decisions when tired, sharing authority, recognizing withdrawal, and addressing resentment before it hardened. Leadership would also have to change with the situation. A medical emergency may require one person to take control. Daily life may need shared decisions so that residents retain some ownership over the place where they live. Autonomy matters when so much of the environment is governed by procedure. People would need choices that were not related to survival. They might choose meals, music, clothing, room, decoration, hobbies, or the plants they cared for. Celebrations would mark birthdays, arrivals, successful repairs, and the first harvest of a new crop. Communication with Earth would remain close enough for conversation. A radio signal usually needs a little more than a second to travel one way. Depending on the changing distance between Earth and the Moon, that pause would be noticeable but manageable. Families could speak across it. Doctors and engineers could consult with specialists. News, books, films, and personal messages could move back and forth once reliable high-capacity links were established, but connection would still depend on infrastructure. Antennas require power, pointing, and maintenance. A settlement on the near side could often communicate directly with Earth. Far-side sight would depend on relay satellites because the Moon itself would block the signal. Redundant paths would matter. If one antenna failed, or one relay moved out of position, another system would need to carry medical data, navigation signals, and personal messages. The emotional meaning of those links would be larger than their technical role. A voice from Earth would cross the distance quickly. Yet the person speaking would remain unreachable by any immediate journey. The conversation could feel intimate and remote at the same time. Earth itself would be present in the sky from much of the lunar near side. Because the moon keeps nearly the same face turned toward our planet, Earth would remain in almost the same region of the sky for an observer at a fixed site. It would shift slightly as orbital geometry changed. Weather systems would move across its blue surface. Clouds would gather and dissolve. Night would spread over continents and then move away again. For a lunar resident, Earth would become both landscape and memory. Someone might recognize the bright curve of an ocean without seeing a single home. A storm larger than a country might be visible, while a family dinner taking place beneath it would remain hidden. Long ago, people used the moon to divide months and measure seasons. A lunar community would reverse that relationship. It would look toward Earth for a reminder of changing weather, turning oceans, and the world where human time first took its form. This connection could support people, but it could also sharpen homesickness. Psychological care would need to be built into ordinary operations. Private counseling links, peer support, recreation, and periods of reduced workload would help residents process isolation before it became a crisis. The physical environment could help as well. Interior design would use more than efficient rows of equipment. Rooms could vary in shape and lighting. Plants could divide spaces and soften sound. Digital windows might show live exterior views or familiar places on Earth. The settlement would need places for gathering and places for being alone. Outside those walls, small impacts would continue. The moon has no atmosphere to burn up tiny particles before they reach the ground. Most micrometeoroids are too small and too widely distributed to threaten a person during a short excursion. But a permanent structure accumulates exposure over years. Outer shielding could break up or slow small particles before they reached a pressure wall. Layers, separated by space, could spread the energy of an impact. Sensors would detect pressure loss, while internal hatches isolated damaged sections. Buried rooms would receive added protection from regolith overhead. The ground itself would not remain perfectly motionless. Apollo seismometers recorded deep moonquakes associated with tidal stresses, smaller events linked to temperature change, impacts, and less frequent shallow quakes. The moon does not have active plate tectonics like Earth, but its interior and crust can still release stored stress. Structures would need flexible connections, secure storage, and foundations designed for local ground conditions. Pipes and cables crossing between modules would require enough movement to survive vibration without tearing free. Most residents might never experience a damaging event, yet preparedness would remain part of the background, just as people in many regions of Earth live with storms, earthquakes, floods, or wildfire seasons. The difference would be that the lunar community could not move far away from danger. Its safe place would always be another part of the same habitat. That reality could make life feel narrow, but it could also deepen cooperation. Every resident would depend on work performed by people they knew. The person cleaning a filter, inspecting a wall, or monitoring a relay satellite would be protecting the entire settlement. Over time, this dependence could become more than procedure. It could become a shared understanding that no one truly lived there alone. A lunar home would be a network of private lives enclosed within one common breath. And once that human network became stable enough to endure, the final question would no longer be only how people could live on the moon. It would be why they would choose to stay. The reason to remain on the moon would not be that living there had become easy. It would be that the work made possible by staying could not be completed during a brief visit. A crew that lands for several days must organize nearly every hour around arrival and departure. Equipment is unpacked, experiments are placed, samples are collected, and the return vehicle waits nearby. Even a successful mission leaves many questions untouched because there is little time to follow an unexpected result. A permanent research community could work differently. Instruments could operate through many lunar days and nights. Seismometers could listen across years rather than weeks. Heat flow probes could measure how energy moves beneath different regions of the crust. Geologists could return repeatedly to the same crater, tracing layers that were formed during separate periods of impact and volcanic activity. The Moon preserves a history that Earth has largely erased. Our planet's surface is moved by plate tectonics, reshaped by water, covered by sediment, and renewed by volcanic activity. Much of the evidence from the earliest solar system has been altered or buried. The lunar surface has also changed, but more gradually. Impact craters, cooled lava plains, ancient crust, and material mixed by countless collisions still carry information from periods that are difficult to study on Earth. A rock collected from the right place can help constrain the age of a basin. A core drilled beneath the disturbed surface can reveal layers deposited at different times. Material preserved in polar cold traps may contain water and other compounds delivered from several sources across lunar history. These are not simply records of the Moon. Earth and the Moon formed within the same region of the early solar system, much of the same impact environment. Understanding when large objects struck the Moon can help scientists reconstruct what was happening around the young Earth during periods for which our own surface retains little evidence. A settlement would allow samples to be gathered with context. Robotic spacecraft are highly capable, but a geologist standing in a field can notice relationships that are difficult to anticipate when a mission is designed years earlier. A subtle change in texture, a boundary between deposits, or an unusual fragment resting among ordinary rocks can redirect an investigation. The value would come from combining human judgment with machines that can travel farther, lift more, and work in places too hazardous for regular surface excursions. Some residents might spend their careers studying only a small part of the landscape. Over time, their familiarity with local terrain would become a scientific instrument of its own. Elsewhere on the Moon, the work could turn away from the ground and toward the early universe. The lunar far side is shielded from much of the radio interference produced on Earth. The Moon's solid body stands between a far side observatory and the transmitters, electronics, and communication systems surrounding our planet. Earth's ionosphere also blocks the lowest frequency radio waves from reaching telescopes on the ground. A lunar observatory would not sit beneath that barrier. This creates the possibility of listening to wavelengths that remain largely inaccessible from Earth. Large arrays of simple antennas spread across the far side could search for faint signals from neutral hydrogen in the young universe before the first generations of stars and galaxies had fully transformed their surroundings. The observations would be difficult. Foreground radio emission from our own galaxy is strong, and the desired cosmological signal is faint. A maintained lunar facility could calibrate instruments, replace failed components, expand an array, and improve it over decades. The far side would need protection as well as equipment. Communication transmitters, power systems, and future industrial activity could disturb the radio environment that makes the location useful. A lasting human presence would therefore bring responsibility for deciding which regions should remain scientifically protected. Settlement would not only open new places for research, it would force people to become careful stewards of environments that had never before required human rules. The Moon could also become a place to test systems intended for more distant journeys. A habitat there would be close enough for frequent communication with Earth. yet far enough outside ordinary terrestrial support to reveal weaknesses in closed-loop life support, surface power, resource extraction, autonomous construction, and long-duration medical care. A machine that produces oxygen from lunar material would demonstrate more than one useful industrial process. It would show whether a crew can maintain complex equipment while depending on its output. A greenhouse that completes many harvest cycles would teach more than how plants grow in reduced gravity. It would reveal how nutrients, microbes, water chemistry, lighting, maintenance, and human routines interact over years. These lessons could inform future missions to asteroids or Mars. They could also improve systems on Earth, especially where water, energy, and materials must be used with greater efficiency. But the Moon should not be treated as an easy replacement for Earth. No lunar settlement, however advanced, would reproduce the living abundance of a planet with oceans, atmosphere, soil, and a functioning biosphere. A protected lunar room would remain an engineered pocket of habitability, supported by constant work. Building such a place would not reduce the importance of caring for Earth. It would make Earth's value harder to overlook. The contrast would be present in every system. On the Moon, air would be measured and circulated. On Earth, forests, oceans, weather, and countless organisms participate in planetary cycles, too large to fit inside any machine. On the Moon, water would be recovered drop by drop. On Earth, it moves through clouds, rivers, ice, ground, bodies, and seas. On the Moon, a small crop requires controlled light, purified water, monitored nutrients, and protected space. On Earth, life occupies environments from warm wetlands to high mountain rock. A lunar resident would not need to be told that a habitable world is rare in practical terms. That knowledge would be built into the maintenance schedule. Perhaps that would become one of the settlement's most important contributions. It would show, with daily clarity, what human life actually requires. Not merely oxygen, calories, and temperature control, but health, privacy, companionship, meaningful work, reliable institutions, and confidence that the systems surrounding a person will still function tomorrow. The first permanent residents would live with limitations that no design could remove entirely. Their radiation exposure would be monitored. Their bodies would adapt to lower gravity. Their movements outside would remain planned. Their safety would depend on machinery and on one another. They would not be conquering the Moon. They would be learning how to cooperate with a place that offers almost none of the conditions their bodies expect. Success would be measured in ordinary continuities. Another filter replaced on schedule, another crop harvested, another damaged component repaired locally, another solar event passed inside shelter, another year of scientific observations preserved and sent home. Gradually, the settlement might become less dependent on shipments. New rooms would be covered with regolith. Workshops would produce a wider range of parts. Water processing would improve. The first temporary corridors would give way to designed for people who expected to remain. There might eventually be residents who knew every route through the base, every sound in its ventilation system, and every change in the ground outside after sunrise. For them, the Moon would no longer be only a destination. It would be the place where their work, friendships, habits, and memories had accumulated. That life would still be difficult. It would also be real, and that is what it would truly take to live on the Moon. Not a single invention, a single landing, or a single moment of courage, but a complete human world maintained inside an environment that never maintains it for us. Above the buried rooms, Earth remains in the lunar sky.